We're not going to learn all our derivative rules today, okay? We're just learning like the first few most basic ones, right? Then we'll go and learn the rest of them throughout this chapter. We'll get better at like drawing pictures of f prime from f, and then we'll learn about f double prime, f triple prime, and how to draw pictures of those from each other and how they work together and so forth, what they're used for.
Is that exciting?
Yep. Okay, so first of all, whose notation am I using right here? Leibniz's notation, okay. So I'm going to write most of our rules in terms of that. So if you want to do this on like the front cover of your notes somewhere, just keep track of all the different derivative rules we have. I find some place that you're not going to lose that you have to make a list of those separate from the rest of your notes, okay. So the derivative of just any constant function. I think we even talked about this in class. Think about it. We just did one where we had a graph of a constant function. What did the derivative turn out to be? Zero. Derivative of any constant function, no matter what c is, whether it's pi, 3, 7/3, it's always 0.
So any constant function like just like
of any number, any horizontal line, if you're thinking graphically, right? Okay. The derivative of c times any function works just like a limit. So how does it work? So let's say you don't know what this function is, but you have a constant multiplied by it. For a limit, how do you do that? You pull the c out in front, and then you multiply by the limit of f. So I'm going to multiply by f prime of x, the derivative of f. See, I'm switching between notations there. It was nicer to write it that way this time, wasn't it? So you'll see me start switching between notations. Okay, so let's see. How about if we have the derivative of f plus or minus g, if you've got a plus or minus g in there. Notice, do I always have to write f of x and g of x? No. Most of the time we did in the past because people lose track of what variables in there. I assume you can handle it right now. It's much nicer if we don't write those f of x's and g of x's in there. This is just like a limit too.
c plus or minus f plus or minus.
What do you mean f? Help me out.
F,
f what?
Prime.
Prime, the derivative
plus or
of
minus
f,
f prime of
plus
g.
or minus the derivative of g. Works just like a limit. It's very easy, right?
Wait,
so if you've got functions and you can think about one plus another one, take the derivative of one, get that done, and take the derivative of the other one separately. This is a much nicer way to do things, okay?
So what's d of x on the bottom?
d of x is just part of the notation. That's
Okay.
part of Leibniz's notation,
Well, you're really not
which is
doing
why when you
anything.
get to multiple variables, it's probably a better notation because sometimes you take the derivative with respect to x, sometimes you take it with respect to z, sometimes you take it with respect to something else.
Like q.
Yeah, exactly. But that helps you keep track of what you're differentiating with respect to, which is going to matter for us too when we get to the end of this chapter.
Oh, so if you're taking it with something else, you'd have dq at the
You could have
bottom?
dx. See, you can do, instead of dy dx, that's like f prime. You can switch it and do dx dy sometimes too. So that helps you keep track. F prime doesn't tell you which way it goes.
Yeah.
So that's one reason I like it a little bit better. Takes a little bit of getting used to though. So. Okay, so how about if you have a power function? We've studied these a lot, right? X squared, x cubed, x to the fifth, or something else. Maybe if you put a 1/2 in there.
Is that over dx?
Yes, of course, you need a dx. That's blasphemy if I don't put that dx in there. Good.
Blasphemy.
All right. So this is where n is any rational. It can even, yeah, any. Let's put any. Let me think. Can I do it to an irrational number? Yes, I can. Any
Or
real
easy.
number.
So not I.
Yeah. Any real number. You can put a decimal in there, a fraction in there, a negative exponent in there. This works for any of that stuff. Turns out there's a nice simple rule for anything. And when you combine this with this, doesn't that work for any possible polynomial? And even more than any possible polynomial it works for. So this is a really powerful rule. And all you do is you bring the n, the exponent down in front, multiply, and decrease it by 1. So simple.
So x in
Such
this
an elegant
situation,
formula.
is x just a number? Or Like right there. Is x, is it a constant number? Or
X is a variable, n is a number, n is a constant.
Okay.
X is variable, n is constant. Good question. Okay. We also have two other rules that we're going to need for this section. Now I have a nice calculator program which seems to have been deleted off my calculator by somebody. I will go get it at home and bring it to you on Monday to show you why this works. So it turns out the derivative of sine, let's just think about it ourselves. We don't even need that calculator program. It's a neat program. So I'll show you guys. So what's sine of x look like? I start at 0 or 1.
0.
2 pi. Start here, go like that, right? Good. That's
That's
f.
a pretty good one, Mr. V.
Thank you.
Is it 0?
Okay, so let's think about the derivative of each point. Slope of the tangent line, okay? Here's the two easiest points to identify right away. What's the slope on each one of those? 0. So let's plot those for the derivative. The slope of the derivative right there is 0, and right there is 0. Okay? Or if we think about like inverse functions of sine and so forth, what's the derivative going to be? Let's just think about this. If we create the tangent line here, we're going to have a positive value, right?
Yeah.
And then if we create the tangent line here, we're going to have a positive value that is bigger or smaller. Is this one going to be bigger or smaller than this one? Bigger. So maybe it's like right here, and maybe that one's a little bit smaller. Maybe it's like right there. And if we create a tangent line, if we create a tangent line right here, it's shallower. Look at that. Let's go create some tangent lines over here, shall we? Right here, it's going to be like real shallow, so it's going to be what slope, negative or positive?
Negative.
Right there. We create another one, it's a little bit more negative. We create another one right here, it's a little bit more negative.
Wait, what are those dots?
Those are derivative values.
Okay, derivative value.
So when I get right here, isn't it going to be like the most negative it can be right there?
Yeah.
So it's going to be like down here, and then once I get here, it's going to start coming up again. If we kept doing it, what is that? Doesn't look perfect, right? But do you see how if you calculate those values, we could use a graphical argument to show that the derivative of sine of x is cosine of x. Is there a way to do it with the limits? Sure, but I think it's nice to look at the graph for that, don't you guys? So I have a program that actually does the tangent line and it shows you and it goes bam, 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 and then it like calculates all the points and connects them and it's really cool. So we'll do that with a couple other ones. I'm so sad it's gone. Disappointing. So the other one turns out for derivative of cosine of x, you might guess they're related. Just look at that real fast. Can you guys try to figure it out? See if it's sine of x. Graph cosine real quick sketch, and think about the slopes and see if it makes sense. Do like 2 points and see if it's actually sine of x. Think about it for just a second. We can handle that. We know our trick stuff. Good.
Yeah, I understand that.
It's negative sin of x.
Let's let other people see it a little bit.
I don't.
That should be minus. Graph it. This guy has a slope of 0 right here. And then it starts out with negative slopes, so it's starting out with negative slopes that get the most negative right there, so this should really be corresponding to that point, shouldn't it? And then over here, we have the most positive slope right there, so that's the maximum up there, and so forth. That's the negative sine of x, not the positive sine of x, isn't it?
So those dots are what the determinant would be at that point?
Yeah, I mean, you can calculate it dot by dot like I did if you need to. That's what I was hoping you would look at. Anyway, so I will show you a couple proofs of this on Monday. I just want to give you some stuff so you can get started. So I will show you the proof of this Monday, and I will show you the proof of one of those on Monday. Those are just graphical arguments, right? They make sense though, they're great. So I'll show you the proofs on Monday,
So with the f
especially
prime
this one. It's so cool.
of x's, do you have to still solve then using the old formula? Because like you had a couple where dc of f of x over d of x equals c times f prime of x.
Yes, you would have to, but
You
there's
still
shortcuts
use
for those
the
too. I just haven't shown
H
you yet.
shortcuts there too.
Yeah, so let's do some examples. That's all we're going to get to today, so I'm going to try to do these real quick. So let's say s of t is negative 18. F of x equals 0. F of x equals x to the 4th. G of x, let's do the cube root. Let's do 1 divided by t squared.
I did not have that right home, so I never moved root on
2 root x.
Yeah.
And maybe just one bigger one.
I just put a
Let's
bunch of
see.
space in it. If I leave a tree laser is
Shouldn't that be number
or just die.
Oh, okay.
I'm not using all the ones in my notes. Okay, let's do all those. We have, how long? We have about, we have 15 minutes, we're good. How long would I expect you guys to be able to do these in? After we know our derivative rules, I expect you to be able to do all these problems in probably under a minute for sure.
All of them? Or
Okay,
just
Yeah,
can
one?
all
you
of
help me
them.
with number 1? I'm stuck.
Negative 18.
It's a constant.
Okay, s prime of t, let's use correct notation. I really need to see the correct notation.
Oh, so it should be
There are
0.
sticklers about that, and there's a reason. Notation in calculus is big time. So the derivative function is, if it's constant,
Negative 18
0.
or 0.
Does it matter what that is? No. So f prime of x here then is 0 still. 0 is a constant, is it not? How about this guy? Here's the rule, bring the 4 down.
4x to the
4x,
third.
yeah.
4x to the third power, you decrease the exponent by 1, n minus 1, okay?
Wait.
How about g of x? G prime of x.
It's the same thing as 1 over x to
Can you
the
do, yeah, x raised to
Okay,
1 over 3.
so you might want to rewrite this first. You're going to be so used to this after we crank through a bunch of problems, but right now this is x to the what?
1/3.
1/3. Rewrite it or think about it in your head like that. I heavily suggest rewriting it for now at least.
So 1/3 x raised to the
1/3 x to the,
2/3.
doesn't it become negative?
Oh,
What's
negative.
1/3 minus 1?
negative 2.
It's negative, and it's got 2/3 left of its magnitude.
Wait, so you,
How about h? H prime of t.
no, I think
You can rewrite this how? Austin, can you help me with this one? How can I rewrite
Sure.
1 over t squared?
That's a good question.
T to what?
T to the half, right? Or no?
That'd be square root of t.
That'd be square root of t. So
Can somebody help him? Negative exponent means move to the bottom or move to the top, right? So you can rewrite it like that. Why would you want to rewrite it like that?
So it can be some negative.
Let me-
Because
yeah,
you
Now you
have
can use that
negative
thing that we
2
just
t
said, right?
minus
N is negative 2
power
now.
of negative 3.
Right, exactly. You bring negative 2 down in front, t to the subtract 1, negative 3 now, which then would rewrite as negative 2 over
T to the third.
t to the third. Okay.
just to the positive.
Yeah.
Oh, because you need that down.
Yeah. You might not need to, it depends on your purpose, but most of the time we're going to be doing that in here. So, okay. F prime of x for this one then.
X to
Austin
the
gave us some help, didn't he? He said this
1/2.
is 2x to the 1/2.
So the answer is x to the negative 1.
1/2 times 2 is what? 1. So x to the negative 1/2. Somebody else. Kate, Allison, can one of you tell me what to do with that to finish it up, make it nice?
Pull out
Negative 1/2. How can I
Wait, where'd
change
your-
that?
With a t.
pull it one out.
I want a positive 1/2. How can I accomplish that?
1
Where'd
over
your
1
two go?
over.
Cassidy says this.
equals
That's still
1
not nice
over
enough to me.
x.
Oh, yeah.
No, you do move it.
1 over square root of x.
I have a question. Where'd your 2 go right there? You have 2x
Half
half.
times 2 is 1.
Oh, okay.
Okay.
And then you subtracted your 1? Yep.
Yeah,
With a
subtracted that up there. 1/2 minus 1 is negative 1/2. Okay. This one, we've got 3 pieces. Does that mean this is harder? No. Okay, you can write this 2 ways. You
I'm
can
gonna
write it.
dy because
Very nice. I like that too. Let's go dy. We gotta say we're differentiating with respect to x. Okay, so just leave that alone. Pull the 3 down. This is a constant, right? Don't get afraid of this fraction. It's just negative 2/3 times what? 3x squared. And then here I'm going to go, okay, just ignore the 4.
Do the NX to the next one.
Okay.
This 3 is that 3, Austin.
Oh,
And then this just sat there the whole time.
yeah.
Nothing happened to it.
I got
Okay.
that now. Hold on here.
So what would I get for this one? Okay.
28x to the 6.
28x to the 6.
Okay, that makes sense.
Okay. Then we had a rule for sine, right?
cosine
What do I do with that negative 2 though?
Pull it out.
Just leave it, right? Just let it sit there.
Cosine
The
x.
rule said take a c times f. The derivative is just c times f prime. And what's the derivative of sine? Cosine of x. Then we do any simplifying. We could cancel there and get negative 2x squared. I don't think we can do anything else.
Got it.
Okay. So do we see how once we get used to these rules a little bit, how easy these are to use? There's only like 1 or 2 derivative formulas that are much of a challenge. So, okay. So, here's what you're going to do for Monday. It's not due till Tuesday. But
Get it.
I'm going to have us probably present some problems on Monday, then I'll show you the rest of the lesson. So I'm hoping to find my computer program. I'll show you a couple of proofs as well though. There are a lot of problems here. You can imagine most of them go pretty fast once you get it.
3 through 24 is a lot.
I've shown you enough to do almost all those problems. So there's some stuff with velocities and accelerations which we're going to talk about on Monday.